Hi everyone. In this video I'm going to cover two topics. The first is a short introduction to what this heading says, short introduction to solving trig equations algebraically, and then we'll work through an example problem besides the one that we're about to go through to introduce this. So one thing to start out with is when we say algebraically, we're actually saying with heavy assistance of a unit circle. So in every one of your Google Classrooms, there should be a unit circle uploaded. Mine is under the important documents category because I feel like it should fall under that. But if you don't have a unit circle handy, go ahead and just quickly Google a unit circle or find one, create one by hand, because we're going to need to heavily reference this and continually reference it over and over and over again. So where we left off last week is we left off by graphing these trig functions. Now at a quick glance, this is a sine function, starts at the principal axis, period is 2 pi, oscillates between 1 and -1. So we can say this is y is equal to sine of x. Or in other words, every x value, or every point on here, is taking the sine of how far over we are and finding the y value. So this is just a whole bunch of ordered pairs. A graph represents a bunch of ordered pairs that are plotted, and this is what a sine function looks like. So with graphs, what we can use them for is we can use them to actually solve equations. So what we're going to do right now is build an equation. So if I want some y value now, if I want y to equal 0.5, I can say 0.5 or 1/2 is sine x. What I've just done now is I've set up a trigonometric or a trig equation. I want to find what x values I need to take the sine of to get 1/2 out for y. So with the graph, we can actually use the graph to solve this, and I'll show you how. We've done this before with lines and with quadratics and different graphs already. But if I want to find where the sine of x is 0.5, I took y and I replaced it with 0.5. So this is actually two equations now. So I want to plot y equals 0.5. And y equals 0.5 looks like a horizontal line, and it's every single y value that is half a unit up from the x-axis. So there it is. So if I want to solve this equation, I find where the blue line intersects the red sinusoidal or oscillating function there. So I can find where the sine of x is 1/2 if I just go through this graph and I identify all the intersections. It equals 1/2 here, it equals 1/2 here, here, and just all the way across. Every intersection of the blue and red is where the sine function achieves a value of 1/2. So if I want to find what these actually are, well, there's an issue here. I don't know what that value is. It's something less than -pi4, or it's something greater than -pi4, I should say. It equals 1/2 here, it equals 1/2 here, and you can get the picture that every single time it's actually a little bit off. My scale is not allowing me to solve this. So this is where we fall back to the algebraic approach. I have to have a perfectly set up graph to be able to solve this equation. If I did something like 0.4, well, we haven't dealt with any ordered pairs of sine that create any values of sine that we can take that create a y value of 0.4. 0.3 also, if I said 0.2, 0.1, those are going to cause issues, so we fall back to an algebraic approach to do this. And that algebraic approach relies directly on the unit circle. So let me go ahead and just get the unit circle so we can see all the values. And let's go ahead and rewrite that equation. We wanted 0.5 to equal sine x. Now in all the examples from here, just one note, we're going to put the trig function first. So we're going to say, when does sine of x achieve a value of 0.5? So it doesn't matter which way we do this. We're just going to put the trig function first always. Now we actually know how to solve this just by looking at the unit circle. And how we do that is if we pay attention to the ordered pairs on the unit circle, we have x values and y values, and we talked about already how the x values are actually the cosine of that angle we're taking, and the y values are the sine of the angle we're taking. So if I want to know where sine is 0.5, I want to find all of the values on the unit circle that have a y value, a sine of 0.5. And I can just go around the unit circle and look at all the ordered pairs and do so. So sine is equal to 0.5, or 1/2 at pi6. So I'm already getting my solutions to this right here. It has solutions of x is pi6. And then I keep working around. Well, I want a height of 1/2. Well, it looks like here's another value of 1/2. That's a y value. So we also have 5 pi 6ths. Now if we keep working around, this is -1/2. This is positive 1/2. And I've gone 2 pi. So this would be, if we're going one revolution around the unit circle, these would be our answers. So we could say right here, sine of x equals 0.5 for x values between 0 radians and 2 pi. If we call it there, we're just doing one revolution around the unit circle and we're set. Now, very quickly in the next slide, we're going to change what we're looking at here. We'll talk about how that works. But this should have provided a little purpose and why the algebraic approach is nice, because I don't know that if we look at from 0 to 2 pi, I don't know that this value right here is pi 6 unless my scale allows it. I don't know that this value right here is 5 pi 6 unless my scale allows it. Now take note also, just a nice connection right now, is those two values that we saw below of negative 1/2 are not intersecting here. That's why it doesn't work there. So it's actually only in this positive chunk, only in this positive chunk, depending on what our domain is. Here we restricted our domain, so we're only looking from this vertical line all the way over to 2 pi. So from this vertical line, that would be where pi, or sine of x, is 1/2. So let's get into one more example. So here we want to find where 2 sine of x is equal to 1 for x values between 0 and 4 pi. We'll worry about this domain, this x value restriction, in just a moment. So if we want to solve this, I don't really know a whole lot about sine functions that are transformed and how they behave in taking values. I don't want to have to worry about multiplying. If I gave you 2 times x is equal to 1, right off the bat you would divide by 2. So we can treat trig functions in the same way. Sine of x is a number, so we can treat it like such. So if we want to start this, the first thing we always want to do is isolate the trig function. So I'm going to divide by 2 on both sides. And here again, how convenient is this? We want to find where sine of x is equal to 1/2. So we already know 2 answers, but let's work through those 2 answers again. If I'm considering a unit circle right here, not a great circle, but I want to find the values where sine, where the y value of the ordered pairs on it is 1/2. Well, we already know there's one point here as a height of 1/2. So this, we said, was pi 6ths. And then we want to find, again, where the height is 1/2. So if we go straight over, there's one of them. We have a right triangle. Here's our second. And we already know that this right here is by going 5 pi 6ths. Almost pi. And always reference that unit circle. Again, pi 6th, 5 pi 6th. Those are the 2 values we take the sine of to get 1/2. So this would be x is equal to pi 6ths. And x is also equal to 5 pi 6ths. So this would be for x values from 0 radians to 2 pi radians. So if we go one revolution around the circle. But what we're asked is we want to go 4 pi. So we want to go through one more period or go around the unit circle another time. So with our sine function, we've done one oscillation. That would be 2 pi. Now we want to go through and do another oscillation through 4 pi. So when we consider this, well, we could graph this and we could go across and set up our axis a lot nicer so we find it. Or we can just consider what's happening as we go from 2 pi, starting here. We won't include it because we've already achieved 2 pi. And I want to go now to 4 pi. So what we're going to do is take pi 6ths right here. And I'm going to go one more revolution around the unit circle, or one more period of 2 pi. So 2 answers here, but also for this domain from 2 pi to 4 pi, we can take pi 6ths and we can add 2 pi to it because we go another revolution around the circle. Well, this is algebra from here. Don't worry about the pi's. I'm going to take pi 6ths and we're going to add 2 pi. Well, I want common denominators. So 2 pi is actually 12 pi 6th if we get a common denominator. So pi 6 plus 12 pi 6 gives me 13 pi 6ths, which is for that second oscillation, that second time around the unit circle. And then similarly, we can do the same thing for 5 pi 6ths. So, and we can say 5 pi 6ths plus 2 pi. So what that would be is that would be similarly 5 pi sixths plus common denominator 6, 12 pi sixths. So we have two more values. 17 pi sixths is what we have there. So we actually have 1, 2, 3, 4 values that it achieves, and this makes sense if we go back to the unit circle or this graph. Let's clean this up. Okay, let's use the mouse to clean this up. So here's from 0 to 2 pi. It achieves it twice. Here's from 2 pi to 4 pi. It achieves it 2 more times. We have 1, 2, 3, 4 values that it reaches 1/2 on the way up and on the way down. So in the end, we would say there are 4 values that sine of 1/2, or 2 sine x equals 1 from 0 to 4 pi. And those 4 values, just to put them all in one place, are x equals pi sixths, 5 pi sixths, 13 pi sixths, and 17 pi sixths. Now, one thing that we could address really quick is you don't just simply look at this and add 4 pi to your answer, because what would happen if we were to add 4 pi to this? I wanted to let you think for a second there. What would happen if we add 4 pi is we go beyond our domain restriction. If I add 4 pi to pi sixths is bigger than 0, so I would be somewhere beyond 4 pi. I'd be 4 pi plus pi sixths. So I only want values of x between 0 and 4 pi that I put in. This doesn't tell me how to find those values. I just have to think about going 1 revolution, 2 revolutions from there, or adding 2 pi to it. So this concludes our first video on an introduction to trig functions and then our first example of solving these. So look for more videos. I'm going to work through a few more examples as we continue this process. Thanks.